all the requirements that we needed to come up with a design, implementation, the testing we have done so far, and lastly, the conclusions and future work, consequent training, ethics, and finally references. It's about Koski. I'm an electrical engineering major.
My name is Seyudu. I'm the engineering major.
What is the motivation behind this project? Basically, all of us probably experience that every day we're running out of power. We were inspired, most what is a veteran, as a soldier. They always running out of power, and where they needed the most moments of crisis, communication.
Actually, for me, I get motivated on this project because when it comes to part of Africa, we don't have electricity to run our system. And also, when it comes to the soldiers in the desert, sometimes they run out of power when it comes to mission. So I developed interest in this project so that we can also bring out a system that can help our soldiers in the field.
What's currently on the market? What is it? It's what is called motion-based kinetic energy. As the name says, it's basically through movement, they charging a device. But again, it's short in battery life. It's bulky. It also relies on a grid, and it's mostly after our survey, it's more functional. What we're bringing, our idea is using an element is called piezoelectric material, which uses a mechanical energy to force a stress, and that converts it to electrical energy, and that combined to a wireless power transfer to charge our device. Basically, by walking and using the stress of our shoe insole, we're charging wirelessly a device.
Isabella, I'm sorry to interrupt,
yes.
but you can use the microphone just for the voice.
Okay, so next is a small explanation. What is the foundation of the system?
Piezoelectric material made of silicon and oxygen. The oxygens have a slight negative charge, and silicons have a slight positive, creating a separation of charge, or a dipole, along each bond. Normally, these dipoles cancel each other out, so there's no net separation of charge in the unit cell. But if a quartz crystal is squeezed along a certain direction, the atoms shift. Because of the resulting asymmetry in charge distribution, the dipoles no longer cancel each other out. The stretch cell ends up with a net negative charge on one side and a net positive on the other. This charge imbalance is repeated all the way through the material, and opposite charges collect on opposite faces of the crystal. This results in a voltage that can drive electricity through a circuit. Piezoelectric materials can have different structures, but what they all have in common is unit cells which lack a center of symmetry. And the stronger the compression on piezoelectric materials, the larger the voltage generated. Stretch the crystal instead, and the voltage will switch, making current flow the other way.
So this is the base of our system, using this material, piezoelectric or piezoelectricity. So what is the social impact? What is the benefits of this project? As mentioned by Wudu, there is extreme villages that they don't have power. They have to walk miles and miles to get some source of power. That will be one of them. Then is during natural disasters. There's people that actually die or more fatalities because of the lack of help and unable to communicate instead of the natural disaster. Hikers that get lost and they can be tracked or GPS device, or as I said before, soldiers that they don't have communication access because they constantly have to carry chargers to able to communicate.
In order to meet our customers' needs, we carry out a survey. We carry out a survey to come out with 5 most important criteria for our system. Based on the 5, we selected 3, which is durability and efficiency. On durability and efficiency, we use it to form the objective tree. As you can see, the rank of the objective tree over there. Also, when it comes to marketing requirements, we base on it on affordability and also easy charging, and also how it can withstand high temperature and eco-friendly. Thus, it will not bring effect. It will not bring effect on the environment. And also, when it comes to engineering requirement, the device is supposed to support multiple devices. That's the output is supposed to support different kinds of devices. And also, when it's supposed to have high magnetic flux linking with the transmission and also receiving, so that we can get maximum transfer of power between the wireless transmission.
This is the overall system description. Basically, we divided into three subunits. The first one is the piezo generator and transmission. The second one is the resonant coupling, which is basically the wireless power transfer technique that we're trying to put in together for this project. And lastly is the charging unit that is going to be connected to the device. This is the schematics layout of this design to write before implementing.
Also, the theory behind our design is the calculation and also the equation behind it. That's for the piezoelectric. In order to get maximum current and also voltage, we arrange the sensor in series and also in parallel, so that we can get minimum internal resistance, whereby we can get up to higher current and also higher voltage. And also, when it comes to the rectifier circuit, we need to rectify the voltage that is coming out of what? The piezoelectric. We use what? Rectification circuit, and also we use inverter circuit in order to change it to what? To AC for transmission again. When it comes to the transmission, when it comes to the receiving circuit, we design boost converter using IGBT, so that we can get maximum output voltage to charge our devices. But when it comes to the transmission circuit, since we are designing, we use ultra inductance in our circuit, so that we can make sure that there's total flux linkage between the transmission and also receiving.
This is the design model description. As I mentioned before, this is the flow of the process of our design. That's why it's starting by the work of the user. Then we're going to decline to storage right before transmitting it. And then this is the resonant coupling, and lastly the charging unit.
Based on the behavior model, we construct our functional model. We divide the functional model into four, which is rectifier and power storage model, inverter model, power transmission model, and also interlink booster converter model. Each model has been divided into two, which is level 0, which explains the model itself, the input and also output, the function, and also level 1 also explains the data, the flow chart of that model. This is our before we can build our circuit, we design it using MATLAB. So based on our design, we're able to measure the voltage that is coming out of the rectifier and compare with the input voltage. And also after everything, we're also able to find out the voltage that is coming out of the inverter, so that we can compare it whether there is any error in it. We were able to design everything, and also we get the actual voltage that we are looking for, which is 15 volts output over there. Thank you. This is the waveform that shows our results based on the MATLAB design. Similarly, this is the input. This is the voltage right after the rectifier. This is the voltage right after input inverter. And then this waveform shows the voltage that goes straight into the portable devices. As you can see, just dump, and then we have constant supply of what voltage over.
This is our current hardware implementation that we've done so far, which is the arrangement of the piezoelectric generator and this rectifier circuit. The risk analysis we conducted by, we have two major constraints, two major problems. The first one was designing, trying to get the desired voltage in the generator unit. And the second one was after, right before charging the unit, we needed to boost our voltage. So we tried several designs, and finally we came up with inter-heat boost converter. The test analysis, so far we have conducted 3 types of test analysis. The first one is the unit test, each component. The second one is the integration testing, which is basically by putting it together, integrating the components, try to get in hardware the desired voltage and current. And finally, so far, we are testing the generator piezoelectric with the rectifier circuit.
On our project schedule, we were able to finish with the design and the testing of the piezoelectric generator. And currently, we are working on the inverter circuit. By the end of the inverter section, we are going to test the inverter. We are going to test the inverter circuit, and then the transmitter circuit, and also the receiver circuit to make sure that they are working correctly. Well, based on our research online, we were able to come out with the most affordable and also high quality component. And based on it, we come out with our total cost as $123.14. This estimation of our total cost.
The conclusion again for a project is aim not for a person who lives in the city or a person who can run to a kiosk and charge a phone or a cafe to charge a phone or device. This project is aimed to help someone who has no access to power, no access to cover the basic needs or moments of crisis during natural disaster, to help them to get in contact or to get help or to get cover the basic needs. That's the main aim of this project. Our future work is we are working and trying to come up with a 3D design implementing design printed custom insole to put the piezo circuit inside the insole. Also, we're trying to put, because the major part that we're gonna consume time is the wireless power transfer. That's one of the major things that we're gonna have to try to accomplish. So we have to accommodate it on the user somehow that it works. And finally, we're gonna try to put we're gonna implement LED lights to indicate the levels of charging in the device. The ethics, the standards and the codes that we use is we rely on IEEE for ethics. We also, since this is aimed for military uses also, so military has their own specifications. Also, we rely on the Manhattan College academic integrity. And finally, some of the ISO and IEECE semiconductor, the piezoelectric use.
When it comes to the constraint, at first, we arranged the sensor, the piezo sensor in series, and we're able to get higher internal resistance, low current. So by doing our research and also coming with the series and parallel circuit, we're able to eliminate the total internal resistance of it. And also when it comes to the boost converter, at first we're using the normal boost converter, which is MOSFET. But through our design, we're able to use IGBT. That's insulated gate IGBT. Insulated gate boost transistors. Yeah. By arranging it into 2, we are able to eliminate the high ripple of the current, whereby we can get a constant supply of current.
This is the references